Hello everyone, this is the last video in conclusion of switching threshold, and the next we'll be moving on to the noise margin characteristics for a CMOS. How does the CMOS inverter responds to a noise margin? So this is the concluding lecture for the switching threshold. What we had done in the past videos is we did some experiments based on PMOS, based on NMOS, and varied the size of the PMOS as an integer multiple of NMOS. Okay, with that we got different sets of values, different data sets. We have the rise delay, fall delay, and switching threshold. So couple of things to observe over here is the first thing to observe: if you vary the PMOS size with respect to NMOS by some few numbers, let's say 2, 3 or 4, the variation in the, or let's say if you vary the switching, if you vary the PMOS size with respect to NMOS between 2 and 3, the variation in the switching threshold is 1.2 to 1.2. It's barely anything. It's 50 millivolts. Okay, so this is a very good advantage for us, and the reason I'm telling this is because when you try to fabricate a PMOS with this size, it might or might not be exactly twice of WN or thrice of WN. It might shift here and there because of the fabrication imperfections that we have. Okay, so because of that we expect the switching threshold to vary, but if you see the variation of the switching threshold with respect to the sizes of the PMOS, it's very few if it's in some range. So if let's say if you take a range of WP by LP in this range from 1 to 3, the variation is about 200 millivolts. But if you take the variation from 1 to 2, let's say if WP is equal to WN and WP is twice the WN, the variation is about 1 to 200 millivolts. So it's in very small range. So that's basically an advantage of having an inverter kind of structure, which we call as CMOS. So that's the first advantage. Also, if you see in this range, for example, a PMOS was designed to be 4.5 times of NMOS. Okay, so we expect the switching threshold will be somewhere between 1.35 and 4 volts. So it will be there is barely any 50 millivolts difference over here. But if the fabrication process makes the PMOS size equal to not 4.5 but 4.7 or even 4 or 5 of NMOS size, then it will be still in the range of 50 millivolts, which is still acceptable for us. Thus the CMOS inverter will still behave what we want it to behave. Okay, that's the first conclusion on this part. Second conclusion, if you look into this one, so there might be a size of a PMOS versus NMOS, where we can see the rise delay is in this case the rise delay is approximately equal to fall delay, but there might be values of PMOS equal to some n of NMOS, in which you can see rise delay is exactly equal to fall delay, and that's what is the basic requirement for a cell which lies in the clock network. I'll come to that in a moment. In this case, this is a situation where you see an equal rise and fall time. So if you design your CMOS to have a switching threshold of 1.2 volts, or roughly about 1.2 to 1.23 volts maybe, there is a possibility that you will get an inverter that has got exactly equal rise and fall time. That has got a symmetry of that particular cell. So that's a very important property that we need for a clock cell. And let's look into the clock cell that I'm talking about. So this is a typical characteristics for a clock inverter or a buffer. I'll take a snippet from one of my courses, which is called as clock tree synthesis. So this lecture is there, or this course is already there on Udemy. This is one of the snippet from that course. We have this huge clock network. On this one, this is the clock source pin, and this is the clock endpoint. Okay, had this been regular buffers, or had this been buffers which have been taken from the other sets, not from this one, had this been a buffer which had been taken like from this one, where WP is equal to WN, or WP equal to thrice of WN or 4 times of WN, the waveform would have been looked something like this. Your rise time and your fall time are different, and as a result of that, your low to high delay and high to low delay, that basically is not the same. That's different. But in this case, the inverter that we have designed, that is basically having a size having a size in such a fashion that the rise delay is equal to fall delay. Okay, in that case you will see that those cases are the ones which we call them as clock inverters or clock buffers. And this is the structure. How does the clock buffer looks like? The PMOS size is equal to NMOS, and it is made equal to NMOS in such a fashion that their resistances match. Okay, so that's what we did in the previous slide. In this case, by setting the VM to 1.2 volts, your resistances of PMOS is now matching more or less approximately equal to the NMOS resistance. And as a result of that, you see this. You see the PMOS being bigger than the NMOS, but the resistances are approximately equal to the same. The reason for the different resistance of PMOS and NMOS is something else which we'll be talking about in the next set of videos, where we'll be talking about dynamic analysis of a CMOS inverter. We'll come to the resistance point from that particular course. In this case, just take it from me that the resistance of the PMOS is 2.5 times greater than NMOS, and so you want a PMOS which is roughly about 2 to 2.5 times bigger than NMOS to achieve a same or similar resistance. By achieving this, by having replace the normal inverters by a clock inverter, so I've already done that. Basically you replace this particular buffer by a clock buffer, so this is what you get. Okay, and the symmetry you basically achieve this exact symmetry. So the reason is that now the rise delay and the fall delay exactly match, and as a result of that, at the output of this particular node, you see a waveform which has got a pulse shape equal to the one that we have sent at the input. Okay, so this is an advantage of having a clock cell or having an inverter which has got a switching threshold lying somewhere at 1.2 volts. Okay, so the question remains is, are the other ones used or not? Yes, they are definitely used, because in this case, by using this one, you save area, and but there's a disadvantage with that, is that you have an unequal rise and fall delay, but this can still be used in some of the data paths. I'll come to the data paths, but the advantage of having this one is that they are of small size. They are regular inverter size, and you can use them in your data path. So for example, if you need if a data path, let's say a timing data path, needs a cell delay which is not 140 picosecond but 37 picosecond, and they don't care about the fall delay, so this is the kind of cell that you can actually plug in and see what do you get. Okay, so let me take an example of a timing path or a data path. So for example, this is one of the snippet again from the same course, from the clock tree synthesis course on Udemy. For example, this is my data path, and the condition over here is, the condition for the slack should be either positive or 0. And for that condition to be valid, you need your data arrival time be less than data required time. But for example, in a situation where your data required time just goes below data arrival time, so in that case you can just reduce the delay, or sorry, you can increase the delay of this data arrival time by plugging the right inverter over here, or the right clock cell over here. So in this case, let's say your data arrival time is expected to be less than data required time, but for some reasons if your data arrival time goes greater than data required time, it means that the theta, this is the combinational delay, it means that the combinational delay is much higher. So in that case, you might want to use a cell which has got a lower delay, which can be achieved by an inverter which looks something in this area. So for example, initially we were using this cell, but you can use, since you have a varied range of cells, you can use any one of this kind of cell to reduce the delay in your data path. You reduce the rise delay in your data path. Okay, fall delay right now we can ignore, because right now let's say this particular circuit depends only on the rise delay. The cell that we are talking about, that's about a rise delay cell. So in order to reduce the rise delay, you just plug in the right kind of cell over there, and you will be able to achieve the data arrival time less than data required time. Okay, so those were the applications of having the different sizes of inverters. So typically in a scenario like this, we will have 5 kinds of inverters. We will have, let's say, INV X1, X2, or let's say this will be calling as INV CX, maybe clock, since it's a clock inverter, we'll call it INV CX. This will call as INV 1X, 2X, 3X, 4X, in that. So we'll have 5 different kinds of inverters, out of which one can be used for a clock cell and the others can be used in the data path. So we'll be talking more about the delays of the cell and how do we exactly use it in the dynamic simulation part. This is, we are evaluating the CMOS inverter robustness or the static behavior of the CMOS. So when we go to dynamic behavior, we'll talk more about more in this language in that particular course. Okay, so that's the advantage of having a regular inverter in a data path. Next, we will be moving into another topic, which is the noise margin. So another characteristics that defines the CMOS inverter robustness is the noise margin. So what we'll do, we'll stop at this point and we'll come back with new set of videos where we first define what the noise margins are and how does the noise margin vary with respect to the inverter that we had just simulated. So let's try to do all this in the next video.